concept using a simple demonstration.
As you can see here, I'm traveling with an average velocity of 1.4 meters per second. I was traveling at a velocity of 1.4 meters per second relative to the Earth. The camera was at a fixed point, therefore its velocity was 0 meters per second relative to the Earth. To find my velocity relative to the camera, you simply subtract the velocity of the camera relative to the Earth from my velocity relative to the Earth, which is 1.4 meters per second. Both the camera and I were traveling at a velocity of 1.4 meters per second. Here I was once again traveling at a velocity of 1.4 meters per second relative to the Earth. The camera was also traveling at the same velocity of 1.4 meters per second in the same direction relative to the Earth. We can apply the same equation here to figure out my velocity relative to the camera. You subtract the velocity of the camera, 1.4 meters per second, from my velocity of 1.4 meters per second to get a relative velocity of 0 meters per second. Here, both the camera and I are traveling at a speed of 1.4 meters per second, but in opposite directions. I am once again traveling at a velocity of 1.4 meters per second relative to the Earth. But this time, the camera is traveling at the same speed of 1.4 meters per second relative to the Earth, but in the opposite direction. Here, we will use the same equation and subtract the camera's velocity of negative 1.4 meters per second from my velocity of 1.4 meters per second. Here, the negatives will cancel out to get that my velocity relative to the camera is 2.8 meters per second. Now we will analyze how different frames of references affect the relative velocity. In the first demonstration, I looked as though I was traveling 1.4 meters per second relative to the camera. In the second demonstration, I looked as though I wasn't moving at all because the camera was moving along with me at the same velocity. In the third demonstration, my velocity relative to the camera was 2.8 meters per second, making it seem as though I was moving faster than I really was. This shows that your frame of reference alters how you see things to be moving. As long as you're not accelerating, the spot at which you are measuring the velocity from can be considered your frame of reference. This is also known as your initial frame of reference. Now let's use a real-life example to illustrate our previous demonstration, and also answer the question of how does one's frame of reference affect the perceived velocity of an object being observed. Let's just say I'm standing at the back of a non-moving pickup truck throwing apples at 15 meters per second. If someone were standing on the sidewalk, how fast would the apples appear to be moving to them? The answer is 15 meters per second because we are in the same frame of reference. Now the truck moves forward at a 20 meters per second, and I continue to throw the apples at the same velocity. How fast are the apples traveling relative to me? And how fast are the apples traveling relative to the person on the sidewalk? To me, the apples are still traveling at 15 meters per second, but to the person on the sidewalk, the apples are now traveling at 35 meters per second. Now I turn around and throw the apples from the back of the truck at the same velocity. How fast are the apples traveling relative to me, and how fast are they traveling relative to the person on the sidewalk? To me, they are traveling 15 meters per second. To the person on the sidewalk, the apples are traveling 5 meters per second. Referring back to our initial question, one's frame of reference can affect the perceived velocity based on where the object started, how fast it is moving, and in what direction it is moving, relative to the velocity of the observer.